In this video, we cover a case study on fuzzy logic. Now, we have discussed previously the basics of fuzzy logic systems, so forth, and then we started discussing a case study on which now we are going to build. The title of that is Dinner for Two People. Okay, dinner for two. So, what is it that we are trying to do in that case? We are talking about two people going out to a restaurant, okay, and then trying to build a fuzzy system that will help them come up with a suitable tip at the end of the food that they have taken. Okay, so you have two inputs depending upon the quality of food and the quality of service. So based on those two inputs, the quality of food and quality of service, you will produce one output which tells you the amount of the percentage or the amount of the tip that you want to give as a reference to the total cost of the bill. And we are using three rules here. So we have three rules, one output, two inputs. We call it dinner for two. Now if you look at the left hand side, we have input 1, okay, and input 2. Input 1 relates to the service quality and input 2 relates to the food quality. And of course, remember we said that it starts with crisp inputs. So input 1, which is the food service, you will give a number from 0 to 10. 0 would meaning poor quality of service. 10 would mean excellent quality of service. Okay, any number between them. Likewise, input 2 is food quality. 0, worse, poor, you don't, want to eat it. And 10 is excellent, you want to maybe come back again. Now, based on these two inputs that can have any value between 0 and 10, both of these are actually fed to the rules. So rule 1 tells you what to do if service is poor or food is rancid, meaning stale, old, smelly. If service is poor or the food is rancid, then tip is cheap. That's rule 1. Rule 2 says if service is good, then tip is average. Rule 3 says if service is excellent or food is delicious, then the tip is generous. Okay. Now each of these rules is separately evaluated and then sent to this concentration part, as you can see, which is trying to combine the outputs of these three. Okay. And then it is defuzzified. So this sigma that you see here is the result, the compilation, the effects of these three rules, and they are then defuzzified and come up with a number which is the amount of tip that you want to give. All right. So first of all, you take inputs and you fuzzify the inputs. Fuzzification, you know how it is. Okay. You relate crisp values to fuzzy values. So once the inputs have been fuzzified, we know the degree to which each part of the antecedent left hand side has been satisfied for each rule. If you look at the diagram again of the OR operator, max, that works. Now remember, we are evaluating the antecedent of rule 3 for tipping calculation. So what does it say? Okay, you have fuzzy inputs. This is how the service quality is represented along with the food quality. Okay, so service, if it is excellent, then it will be at the top, otherwise below. And what we have is the input coming from the two people who have gone there. They say service is 3 on a scale of 1 to 10. So then you will take that point off and come to the next one. So you have given 3 to the quality of service and 8 to the quality of food. It happens every day. Sometimes you don't like the food, sometimes you do, sometimes service is not good and so forth. The service is at level 3 out of 10, food is 8 out of 10. And the rule says either, service is excellent or, so this or translates into the max of these two values. So food 8 translates into 0.7, service quality 3 translates into 0.3, and we take the maximum of this, which is 0.7. So result of the fuzzy operator here is 0.7. Now, as I said, because of the higher values, max takes the bigger of the two values. Now we apply the implication. What does it mean? Implication, remember the left hand side of the rule, and implies the right hand side. We also need to take into consideration sometimes the weightage of the rule. In this case, the weightage of rule can be anything between 0 and 1. We take it as 1. So all rules have equal weightage in this particular case. All right. So once we have that assigned, the implication method is implemented to each rule, and the consequent of these, the right hand side is a fuzzy set represented by a membership function, okay, which after weighing appropriately these linguistic characteristics are attributed to it, and we come up with a single number. So the input for the implication process is a single number given by the output antecedent, and the output is a fuzzy set. Implication, by the way, is applied for each rule, and typically we can use various options, but in this case we are going to use the minimum operator, okay, to perform the implication, which will truncate the output as we see in the figure. So we have, this is rule 3 again, service quality, food quality, and then we take the minimum of these two, and as you can see, the consequent is in front of you, the result of the implication. Now I must also add that on the left you will see the OR operator that comes up with the max of these two, and then you have the minimum for the implication operator. Now we aggregate all outputs. So since decisions are based on the testing of all the rules in a fuzzy inference system, the rules have to be combined in some manner to decide what to do, and that's what aggregation is. Remember that summation part I showed you earlier on? So aggregation is a process by which the fuzzy sets that represent the outputs of each rule are combined into a single fuzzy set. That's what it means. And it only occurs once for each output variable, just prior to the final step of defuzzification. So the input of aggregation process is the list of the outputs that received after applying the implication process for each rule, and the output of the aggregation process is one fuzzy set for each output variable, which is only one, in this case the tip that you want to give. Well, if the aggregation method is commutative, as it doesn't matter which sequence of rules we apply, that becomes irrelevant, not important. And by the way, any logical operator can be used to perform the aggregation, max, probabilistic, or sum each of them, each of the outputs, and so forth. In the diagram, all three rules have been placed together to show how the output of each rule is combined or aggregated into a single fuzzy set, and whose membership function assigns a weightage for every tip value that we need to. So we have three rules, each row showing one rule, and then each column tells you what is happening. So for the first rule, there's an operator which says OR. So OR takes the maximum. Rule number 2 has no other implications. You takes whatever it is, that's the output. And the third one says, once again, service is good or food is. So that means the OR operator, which is the max, and then you get the third column outputs for each. And then you apply the implication. That's the fourth column. And at the base of the fourth column is the final aggregated output. Now there are several ways of doing that. One is the most common, okay, the defuzzification part is a fuzzy set, of course, and output has to be a single number, and typically what we use is a centroid function, okay, which aggregates the fuzzy set into a single range. So centroid is one of the most popular methods used. There can be others. There can be centroid, as I said, by sector, middle of maximum, average, max of the three or any number of rules that you have. In this case, we're going for the central value. That's what I mean by centroid. So if you look at the diagram again, remember the fourth column, the very last line, that is what's shown here again. We need to apply this defuzzification using centroid, and that centroid in the middle, which is the central value of each of these, it comes up with a number given as 16.7%. So this is the output we're talking about. We gave 3 to service and 8 to the food quality, okay. We have come up using a fuzzy based system. We have come up with the result that tip has to be 16.7% of the total bill. Okay, so this is what we're trying to give. And The reason we've gone through this exercise, by the way, is you go everywhere, anywhere in the world, okay, tipping is a very sensitive thing. You must remember that. So if we have come up with a fuzzy system that tells you, given your set of inputs, this is what your tip should be, 16.7% of the total bill. Now, we have worked out a MATLAB implementation of this as well. A MATLAB is a piece of software that we'll see. We will put these values in there. We will see each step, how it is applied for each rule, and then implication, and then aggregation, and then defuzzification. On the screen, you can see the front end of this tool. What you need to do is, in the command prompt, enter the name of the tool fuzzy as shown. So once you do that, the fuzzy logic tool interface that opens up. Now briefly again, we are working on a dinner for two example. We have two inputs for service and food quality. We have three rules. I've explained them before. A service is poor or food is rancid, then tip is cheap. Service is good, then tip is average, and service is excellent or food is delicious, then tip is generous. And then with the aggregation of these three rules, finally we come out with the output defuzzification. So the inputs to the system are crisp numbers, and the output itself is also a crisp number, having gone through all the transformations. Now, as there are two inputs and one output of the dinner problem, service and food, and of course output is a tip, in the fuzzy inference system, for the rule we use the OR method, the maximum, when it says the food quality is excellent or the service is good, right? So that OR is represented by the max of those two. For implication of each rule, we use the min operator, and for the aggregation, combining of these rules, we use the max operator. For defuzzification, okay, at the end of the process, the defuzzification, we are going to use the centroid method for demonstrating the problem. Now we are going to set the membership function of the two inputs, service and food quality, and of course the output. Now, already said before, the input membership is in the range 0 to 10 for both food and service, right? The service has itself three linguistic variables. The service can be poor, it can be good, and excellent. Now we need to assign various numbers to each of these three, and we are going to use the triangular membership function called trimf. Okay, so that actually assigns suitable values to the value poor, good, and excellent. These are the linguistic variables used. We normally use them. You can see that happening. Now the food membership function once again is divided into three linguistic variables. The food can be rancid, which means stale, bad, is smelly, and average, and delicious. And once again, these three linguistic variables need to be translated on a scale of 1 to 10, which has just been done here for you using the triangular function. And also for the tip, there are three linguistic variables for this, which means cheap tip, average tip, and generous tip. However, in this case, the range is between 0 and 25% instead of 1 to 10 in the case of the two inputs. What this means is that the minimum tip is 0% of the total bill, to a maximum of 25% of the total bill. So we need to define, associate cheap, average, generous on this scale. Let's come to rules. We have defined the three rules, as you can see up there. We've already done that for you. So if service is poor and food is rancid, then tip is cheap. That rule number one. Rule number two is, if service is good, then tip is average. And if the service is excellent and food is delicious, then tip is generous. And this is how we actually define the rules. All right, let's go to the rule viewer now. That's very interesting. In the rule viewer, we can see the inference of the rules as provided by the inputs shown below. You can see these vertical lines, the red ones. We can move them around. We can move them from left to right. What they're doing is, let's say look at the first column, which says service. At present, the service level is 3, and in the second column, the food is 8. You know the number that you've given, and correspondingly, we can see the tip value. Now, if I move this vertical red line, I can move it to the left or the right. So this will tell us if I move it to the right, okay, the service value improves. And if I keep the food value where it is, you can see the effect of the service that will only service, keeping the food value there, you can see the effect on the tip value. And by moving it to the left or right, likewise, food, the one in the middle. So I can play around with these, and that's the quality. That is the idea we're trying to tell you. This simulation help you actually demonstrate what will happen if the service quality is 0 or 1, or let's say 9, and the food quality remains good, for instance. Then the tip, whatever that tip is, and there's a maximum value 25%. So by moving around these two, this fuzzy tool itself actually is doing the things in the background for you. So I hope you find it interesting and useful. We'll use this tool again in another case study as well. Now, this rule viewer, and there's another one also called surface viewer. That's another view of the same things in a 3-dimensional form. In this video, I'm not going to talk too much about it, but if you play around with the rule viewer and the service viewer, you can see how these two are related. Food and service affecting the tip value. The vertical line is the tip, as you can see, from say 0 to 2025, okay, and then on the one of the axes is food, 0 to 10, and on the other axis it's service. So 3D view of the application of these rules. So in the end, I hope you found this interesting, and to be honest, of all the things I've done so far, myself also, the best part is the simulation, which tells you what actually happens. And this is the real exciting part. I'm pretty sure this will give you a lot of excitement, and you will tend to use this and use it for other applications as well. Thank you very much. We'll see you again.